Hello again. This lecture is on kernelization. So this is where we see a mathematical way to analyze preprocessing algorithms. So in this course we are looking at exponential time algorithms, NP-hard problems, so problems where we expect to take exponential time to solve them. But here in this lecture we are going to see what can we actually do in polynomial time. So maybe we can solve parts of an instance, make optimal decisions for some vertices, and so we'll see how efficiently and effectively we can do this. And so we are going to see a few preprocessing algorithms or kernelization algorithms for several problems, like for vertex cover, for Hamiltonian cycle, edge click cover. And so while doing this, we are also building this theory about how to design kernelization algorithms. Okay, let's start with vertex cover. So as you remember, a vertex cover of a graph is a subset of vertices, such as the three red vertices here, that cover all the edges of the graph. So for every edge of the graph, we need to have that at least one of the endpoints has been selected into our vertex cover. Now, the input to the vertex cover problem is a graph G and an integer k. And the question is whether G has a vertex cover of size at most k. And for the parameterized version, we use k as the parameter. So in this example graph, of course, the red vertices form a vertex cover of size 3. So if this is our input graph and k is 3, then this is a yes instance. Okay, let me give you a few examples. So I'll ask you to solve vertex cover on these examples, and it's very helpful if you stop the video here and try and do this yourself. So you try to solve the vertex cover problem on this example graph and see how far do you get by doing optimal decisions, by, for example, noticing that, well, the vertex E doesn't cover any edges, so we might as well get rid of it, and use some reasoning to also handle the other vertices of the graph. So this is the first example we'll see. So we just need to decide whether this is a yes instance for vertex cover or not. And if you want, you can already think about any general rules you might encounter when handling such an instance. Okay, so let's see how we could solve vertex cover for this instance. So we have our graph here, and k is 4. Okay, so I already observed that, well, E doesn't cover any edges, so any vertex cover that contains E can be made into a vertex cover that doesn't contain E. And since we are looking at the minimization problem, so we want to check whether G has a vertex cover of size at most k, we can just remove E from the graph. We will never put it into a vertex cover, and we don't need to remember any information about E. Okay, so E had degree 0. We could easily handle it. What about degree 1 vertex, such as the vertex B here? So B has degree 1, and what does it do? So if we add B to our vertex cover, this vertex will cover the edge, well, B will cover the edge AB. That's the only thing it can do. But we can notice that, well, there's another vertex, vertex A, that covers the same edge. So it can take the role of B, so it can cover the same edge, and it even covers many more edges. So it seems that we might want to prefer to add A to the vertex cover instead of B. So more formally, we can reason that take any vertex cover that contains B. Now we transform it into a new vertex cover, where we remove B from that vertex cover and add A instead. So the size doesn't increase, and we still cover the same edges as before, maybe even, well, we still cover the edges that are covered by B. because A covers all of those. So what can we then say? And of course we have the property that if we look at the edge AB, one of the two endpoints at least must be in the vertex cover. So, and it seems that A is the better choice. So we could add A into the vertex cover and not B. So what remains to be done? So we can tick off the edges that we have already covered. So basically it's all those edges that are incident to A. Now we are left with a complete graph on 4 vertices. Oh, sorry. K also decreased now. It decreased to 3. Okay, in a complete graph on 4 vertices, can we find 3 vertices that cover all the edges? And the answer is yes. It doesn't matter which ones we take. So take any 3 vertices of this complete graph on 4 vertices, and we'll get a vertex cover of size 3 in the remaining graph, so 4 in the original graph. And then after taking these 3 vertices, k decreases to 0. And here you can see that we have found a vertex cover of size 4. So this is a yes instance. It's a yes instance, and we didn't have to go through all subsets of vertices or 4 vertices to check this. We could reason and make some optimal decisions, especially for our degree 0 vertices and degree 1 vertices. Okay, let's try this again. So here we have another graph, and k is 7. So we need to check whether this graph has a vertex cover of size 7. So let's handle our degree 0 vertices and just remove them. So we don't need them. They will not help us cover any edges. Now we have this degree 1 vertex A, and again we reason that, well, the vertex D covers all the edges that A covers and more. So we'll add D to the vertex cover, but not A. Okay, so this covers some edges. K decreases to 6. What now? The instance still looks very complicated, so I'm not comfortable going through all sets of 6 vertices of the remaining vertex set. But can we do something? Okay, so let's see. K has decreased to 6. Look at the vertex N. So on the bottom here. So the vertex N, what does it do? Well, it covers all its incident edges if we add it to the vertex cover, and it's incident to 7 edges. Okay, suppose we do not add N to the vertex cover. But then to cover its incident edges, we have to add all its neighbors to the vertex cover. It has 7 neighbors. So that would exceed our budget because we are only allowed to put 6 more vertices into the vertex cover. So we conclude that, well, if N is not added to the vertex cover, then we cannot cover this graph with another 6 vertices. So we need to add N to our vertex cover. So we do add N to our vertex cover. K decreases by 1. Okay, what happens now? So M covers 1 more edge, but L covers the same edge and more. So we can think of this as, so after deleting those vertices that we deleted from the graph or that we added to the vertex cover, so after deleting them, M will now have degree 1. And in that graph, it makes much more sense to add L to the vertex cover and remove M from the graph. So K decreases to 4. So what happens now? Do we have a degree 5 vertex? Yes, the vertex I has degree 5. And K is 4, so if we don't add I to the vertex cover, all its 5 neighbors must be in the vertex cover. So we conclude that we can add I to the vertex cover. K decreases to 3. It's getting a bit messy, but bear with me. So what happens now? We still have the vertices J, K, H, G, E, and F. Okay, but F now has degree 4, and K is 3. So we again conclude that we should add F to our vertex cover. K decreases to 2 now. Do we have a degree 3 vertex? Yes, indeed we do. H has degree 3, so we add H to our vertex cover. K decreases to 1. E now has degree 1, so G as well. Doesn't really matter which one of those two we add to our vertex cover. Let's choose the vertex G. We don't add E, this is covered. K has decreased to 0, but we still have the edge JK that hasn't been covered. So we kept making optimal decisions, but we weren't able to cover everything, so we conclude that this is a no instance. Okay, so I said that we kept doing optimal decisions, but of course one would need to prove this. And that one would need to prove that all the reasoning that we did, so the rules that we applied, are correct. Okay, so these rules that we keep applying, those are called simplification rules. So let's just revisit what have we done. So we use the rule that's the degree 0 rule, and that says if there's a vertex in the graph that has degree 1, then we remove this vertex from the graph. Okay, and now we need to prove that this rule is correct. So what does correctness mean? That it shouldn't happen that we change a yes instance into a no instance, or that we change a no instance into a yes instance. So before applying the rule, we have some instance. After applying the rule, we have some other instance. And so the two of them should be equivalent. So either both of them are yes instances, or both of them are no instances. Okay, so to prove that the degree 0 rule is sound, soundness is the same as correctness, we need to prove that the input is a yes instance if and only if the output is a yes instance. So the input to this rule and the output to this rule are equivalent. Okay, so first suppose that the output is a yes instance. So we'll prove that the input must have been a yes instance. And suppose that S is a vertex cover for G minus V of size at most K. But then S is also a vertex cover for G, since there are no edges incident to V. So all the edges that are covered in G minus V are also the edges of G. So all the edges of G are covered by using S as a vertex cover. Okay, so we prove that if the output is a yes instance, then the input is a yes instance. So let's prove that if the output is a no instance, then the input is a no instance. And this covers then all the cases. Okay, so for the sake of contradiction, so if the output is a no instance, for the sake of contradiction, assume that the input is a yes instance. And consider a vertex cover S for G of size at most K. But now S minus V is also a vertex cover of G, and it's also a vertex cover of G minus V. And it has size at most K, and therefore we have a contradiction because we suppose that G minus V, K is a no instance. So the simple reasoning shows that the degree 0 rule is sound. Okay, let's look at our next rule. So the next rule says that if V is a degree 1 vertex, then what is this notation? So we remove from the graph G, we remove V and its neighbors. So this is the closed neighborhood of V. It contains V and all its neighbors. So V has only one neighbor, so we remove V and its neighbor from the graph, and we decrease K by 1. Okay, so V is our degree 1 vertex. Let's say U is its neighbor. So what happens now in G is that V gets removed and U gets removed. So this also implicitly removes all the edges that are incident to the two vertices. And K decreases by 1. So this is the only thing that changes in the instance. But of course, we are thinking about adding U to our vertex cover. Since we are only talking about the decision problem here, we just need to produce an equivalent instance. But so intuitively, we are thinking of adding U to the vertex cover. Okay, so to show that the degree 1 rule is sound, if U is the neighbor of V in G, then of course the closed neighborhood of V is U and V. Now, if S is a vertex cover of G of size at most K, so if the input is a yes instance, then after removing U and V, so from S, we get a vertex cover of the graph G minus the closed neighborhood of V, and it has size at most K plus K minus 1. Why does it have size at most K minus 1? Well, because in S, either U or V must have been in S to cover the edge UV. So after removing the set UV from S, we get a vertex cover. We get a set of size at most K minus 1. And also, this set covers all the edges of G minus the closed neighborhood of V, just because we have already removed all the edges that were covered by U and V. And all the remaining edges were covered by the remaining vertices of S. Okay, so what have we proved now? So we proved that if G is yes instance, then the output instance is also a yes instance. So the output instance is G minus the closed neighborhood of V, comma, K minus 1. Okay, so now we are going to show that if the output instance is a yes instance, then the input instance is also a yes instance. So if S prime is a vertex cover of G minus the closed neighborhood of V of size at most K minus 1, now adding U to this vertex cover covers all the edges of G, because U covers all the edges that we removed by removing U and V from the graph, and the remaining edges are all covered by the vertex set S prime. So, and we added one vertex to S prime, so we get a set of size K. So the set of size K is now a vertex cover of G, and this shows then that the input must have been a yes instance. Okay, so we showed both ways, so we conclude that the degree 1 rule is sound. Now we have the large degree rule. So, and that one says that if we have a vertex with degree more than K, then we can remove it from the graph and decrease K by 1. So intuitively, we would add this vertex to our vertex cover. Why is this rule sound? Well, if we have a vertex cover S of size at most K, and V is not in S, then the neighborhood of V must be in S. And this contradicts that the size of S is at most K, because V has more than K neighbors. So we would exceed our budget if we actually would not add V to our vertex cover. and that's why it's an optimal choice to add V. Okay, we have one more rule here, which is the number of edges. It says that if the degree of every vertex is at most k, or in other words, if the previous rule didn't apply, and the number of edges is more than k squared, then return no. So we determine that the instance is no instance in that case. Why is that? Well, imagine any vertex cover S of size at most k. So here we have a set S, and its size is at most k. And now each of these vertices has degree at most k. But then, since each of them can cover at most k edges, in total they can cover at most k squared edges. And if we still have more than k squared edges, then we know that we have no instance. So to prove that this rule is sound, we assume that the degree of every vertex is at most k, and the number of edges is more than k squared, and suppose S is any vertex cover of size at most k. But then we have that S covers at most k squared edges. However, the number of edges is at least k squared plus 1, therefore S is not the vertex cover of G. So therefore this rule is sound. Okay, so putting all of this together, we get the following pre-processing algorithm. So the input is a graph G and an integer k, and the output will be a graph G prime and an integer k prime, such that, well, we have equivalent instances. So G has a vertex cover of size at most k, if and only if G prime has a vertex cover of size at most k prime. Okay, so our algorithm does the following. So first of all, it copies G and K into G prime and K prime. Now it executes all these simplification rules until none of these simplification rules applies anymore. So we apply these simplification rules to the graph G prime and parameter K prime. Now when no simplification rule applies anymore, then we return the graph G prime K prime. So the graph G prime and the integer K prime as our returned instance. Okay, so I think it's quite easy to see that each of these simplification rules takes polynomial time. But what effect or how effective is this pre-processing algorithm? And the main idea is here that we would like to study pre-processing algorithms mathematically and quantify how effective they are. Because, well, you see, so this pre-processing algorithm might do something to our instance. It might actually return the input instance. But we somehow want to quantify, well, how much does it do for us? And we can take a first try here. So let's say we say that the pre-processing algorithm for problem pi is nice if it runs in polynomial time, and for each instance it returns an instance that is strictly smaller. So we give it an instance and we say it's nice. It's not the algorithm is nice if it always gives us a smaller instance. But this turns out to be not a very good definition, because now executing this pre-processing algorithm a linear number of times will reduce the instance to a single bit. In the single bit, it encodes yes or no. So such an algorithm, if we just take this polynomial time algorithm, execute it a linear number of times, by doing this, we would then solve pi in polynomial time. But we don't expect that we can do this for NP hard problems. So this is not possible unless P equals NP. Therefore now we need a different measure of effectiveness. And what we will do is we will measure the effectiveness in terms of the parameter. So we will ask, how large is the resulting instance as a function of the parameter, or in terms of the parameter? So will it return instances of size 2 to the power k? Will it return instances of size 4 to the power k? Will it return instances of size k squared, maybe even a polynomial in k? So, and then we can really compare these preprocessing algorithms. So then we can say maybe a preprocessing algorithm that returns an instance of size k squared or order k squared is better than one that returns an instance of size order k cubed. Okay, so our VC preprocess algorithm turns out to produce equivalent instances of size order k squared. Okay, let's see. So first of all, we have already shown that the simplification rules are sound. So the input instance is equivalent to the output instance. So that's good. Now, because of the number of edges rule, we know that the size of E prime, so the number of edges of the output graph, is at most k prime squared. But also we can observe, if we go back to the simplification rules, that k prime never increases. We will never increase k prime. So k prime is at most k. So therefore the number of edges of the output is at most k squared. Now we also preprocessed, so bounding number of edges is not enough because, well, in general, we could have lots and lots of degree 0 vertices in our instance. But we preprocessed them, so we got rid of degree 0 and degree 1 vertices. And so each vertex in V prime has degree at least 2 in G prime. Now, by the handshaking lemma, so the sum of the vertex degrees equals twice the number of edges, and we have upper bounded the number of edges. So the sum of the vertex degrees is at most 2k squared. And so this implies now, since every vertex has degree at least 2, this implies that the number of vertices is at most k squared. So the number of vertices in the output is also at most k squared. So we have upper bounded number of vertices and the number of edges by k squared. So we get an output instance of size order k squared. Okay, so we can say that this is a preprocessing algorithm that returns an equivalent instance of size order k squared. And so we are now very close to the definition of kernelization algorithms, or kernelization. So a kernel, or kernelization for a parameterized problem, is a polynomial time algorithm which, for any instance with parameter k, produces an equivalent instance of the same problem. So the input problem pi here and the output problems, those are the same problems. And so the output instance has parameter k prime, and we need that the size of the output instance is upper bounded by a function of k. And also the resulting parameter k prime is upper bounded by a function of k for some computable function f. And so we refer to this function f as the size of the kernel. We do not formally require that k prime is at most k, but this will actually be the case for many kernelizations. So we observe that for the VC preprocess algorithm, k prime never increased, so we had automatically that k prime is at most k, and this is the case quite often. Okay, so kernels are not just polynomial time preprocessing algorithms where we are able to upper bound the size of the output instance by a function of the parameter. So VC preprocess is an O-squared kernel for vertex cover. Let's look at another example. So let's look at the Hamiltonian cycle problem. So what is a Hamiltonian cycle? Well, it is a subgraph of G that is a cycle that reaches every vertex in G. So it's a cycle on n vertices. That's a subgraph of our input graph. Okay, so our input is a graph G. And as parameter here, I choose the size of the smallest vertex cover of G. So K is the size of the smallest vertex cover of G. And the question is, does G have a Hamiltonian cycle? Okay, so we'll try and design a preprocessing algorithm for this problem. And so a general thing we can do is we imagine a very, very large instance where the parameter is tiny. And we'll think about whether we can preprocess such an instance. Okay. So let's see. So the parameter is tiny, which means we have a very small vertex cover in our graph. As an aside, we know we have a very small vertex cover, but we might actually not be able to compute it because, well, vertex cover is an NP-hard problem. Our preprocessing algorithm is supposed to run in polynomial time. So this vertex cover exists somewhere, but we are actually not able to find it. Okay, so but our graph, so how do the edges of the graph look like? Let's say we have a vertex cover of size 2, and then we have lots of outside vertices. So we have a huge graph, but all the edges are either inside the vertex cover or connected to at least one vertex of the vertex cover. So we don't have edges like this, right? We can't have this. Okay, now the question is whether this graph here has a Hamiltonian cycle. So we have to, so our cycle has to go through each vertex exactly once. But this doesn't seem to be possible for this graph because, well, our cycle needs to have many consecutive vertices that are outside of the vertex cover. And that's not possible because we don't have edges outside of the vertex cover. So, more general, if we look at the vertex cover, the complement is an independent set. Now, our Hamiltonian cycle, let's say it arrived at some vertex V here, and now where does it go next? It goes to a neighbor. So neighbors could be in the independent set, it goes there, and now where does the cycle go now? So it has to go to a neighbor, so it cannot stay in the independent set because there's no edges joining two vertices in the independent set. So now it has to go back to the vertex cover. And then it can stay in the vertex cover. There might be edges inside the vertex cover. And then it might go out again. But now as soon as it goes out, it has to go back into a new vertex from the vertex cover. Now it goes out again, let's say, and now it goes back into the vertex cover, into a new vertex. But if the vertex cover is too small, then it has nowhere to go once it reached the independent set several times. So we should be able to exploit this somehow, right? So if the vertex cover is small, then we don't have a Hamiltonian cycle. So we know we have a no instance. Okay, so I already mentioned that we do not actually know a vertex cover of size k. We do not even know the value of k. So what we know here is just the input. So the input is what the algorithm gets. So the algorithm just gets a graph. Now the parameter is the size of the smallest vertex cover of G, but we don't know this value. What can we do? Well, we can actually approximate the vertex cover problem. So we can obtain a vertex cover using an approximation algorithm. And we already saw that there exists a 2 approximation algorithm for vertex cover. And it produces a vertex cover of size at most 2k in polynomial time. Now, okay, so we run an approximation algorithm. It returns us some vertex cover, and that vertex cover is not too large compared to k. So it gives us a vertex cover C, and its size is at most 2k. Notice that we don't even know what k is, but we know that C is at most 2k. Now, the remainder of the graph is an independent set. Okay, and we observe that, well, the Hamiltonian cycle cannot have 2 consecutive vertices in the independent set, and that's why if the size of I is more than 2k, then we know that we have no instance. Or if the size of I is more than C, we don't actually know what 2k is. So you can say if the size of I is more than C, then we have no instance. Okay, so we can obtain a kernel with at most 4k vertices with the simplification rule too large, which computes a vertex cover of size at most 2k in polynomial time. And then if twice the size of the cover that we get is less than the size of V, then we return no. Okay, so we'll get a kernel with 4k vertices. We have to upper bound the size of the resulting instance. So our graph contains vertices and edges. So how many edges can we have when we have 4k vertices? Well, the number of edges in general can be upper bounded by a quadratic of the number of vertices. So we have order k squared edges. So we can then say that the Hamiltonian cycle, parameterized by the size of the smallest vertex cover, has a quadratic kernel.